Best time to buy and sell stock. Have you ever wondered how top engineers spot patterns that lead to big wins? Best time to buy and sell stock is not just a must-know pattern mastery 100 question. It appears in almost every Fong interview loop and stumps over 40% of applicants. Mastering this problem gives you an edge in any technical interview because it teaches you to recognize profit opportunities, optimize for efficiency, and think like a Wall Street pro. Ready to discover the secret? Let's dive in. Let's break down the problem. We're given an array where each element represents the price of a stock on a given day. Our job? Find the maximum profit we can achieve by choosing a single day to buy and a different day in the future to sell. If there's no way to make profit, return 0. No short selling, and you can't sell before you buy. Let's assess our options. A naive brute force solution would check every possible pair of buy and sell days, but that takes O(n)² time, not scalable for big inputs. Instead, can we track the lowest price seen so far and always check the profit if we sold today? This only needs a single pass and O(1) extra space. Super efficient. Remember, always buy before you sell, and update your max profit as you go. Here's the structure of our plan. Start with variables for the minimum price so far, set to infinity, and maximum profit, set to 0. Loop through each price in the array. If the current price is less than the minimum, update the minimum. Otherwise, calculate the profit if we sold today, and update max profit if it's higher.
Let us try to implement it using solution 1. We start by defining the solution class. This is the container that will hold our method. Then we declare the max profit method. It receives an array of daily prices and aims to return the best possible profit from one buy and one sell. Next, we set up two variables. Min starts at the largest possible integer, so the very first price will immediately replace it. Profit starts at 0 and will store the highest profit we have seen so far. From there, we loop through each price P in the list. Since we visit each price once, this step runs in O(n) time. Inside the loop, we first check whether today's price is lower than any price we have seen before. If it is, we update min. This is like saying, this is the best day to buy so far. Let us remember it. Otherwise, meaning the price is not a new minimum, we check whether selling today would give us a better profit than we have seen before. If today's price minus the best buy price, which is min, is greater than our current profit, we update profit. This is the moment we discover a more profitable sell day. That closes the loop. By now, we have examined every possible buying and selling opportunity in a single pass. And finally, we return the highest profit we found. If prices only moved downward, that value will stay at 0. That means no profitable trade existed. And that is how this algorithm works. It tracks the cheapest price as we scan the list. Then it updates the maximum profit whenever selling on the current day beats our past results. Efficient. Simple. Clear. Check. This test case evaluates the maximum profit achievable from a single buy and sell stock transaction. Prices equals 7, 1, 5, 3, 6, 4. Each value represents the stock price on a different day. The task is to buy once, sell once later, and maximize profit. Start at 7 as the initial minimum. No profit yet. Move to 1. This becomes the new minimum since it is lower. Next is 5. Selling here after buying at 1 gives a profit of 4. Then 3. Still above the buy price, but the profit would be 2, which is lower than before. Then 6. Selling at 6 after buying at 1 gives a profit of 5. That is now the highest so far. Finally 4. The profit would be 3, which is not better than the current best. The largest profit encountered is 6 minus 1, which equals 5. The output is 5, matching the expected 5. This confirms that the solution properly tracks the minimum price and the maximum possible profit throughout the scan. Now let us try another implement approach using solution 2. We begin by defining our solution class. This is the container that will hold the logic we are about to walk through. Then we declare the max profit method. It receives an array of daily stock prices. Next, we set up two key variables. Cur tracks our current running profit streak. Best keeps the highest streak we have seen so far. Think of it like keeping a running score and remembering your all-time high. From there, we loop through the price list starting at index 1 so we can compare each day with the day before it. This loop touches each day once. That gives us O(n) time. Inside the loop, we calculate the daily change D. This is today's price minus yesterday's price. A positive value means an increase. A negative value means a drop. Then we update our running streak. We set cur to the maximum of 0 and cur plus d. If adding today's change keeps our streak positive, we continue it. If the streak would drop below 0, we reset it to 0 and start fresh. It is just like tossing out a losing streak and beginning again. After that, we compare our current streak to our all-time best. If today's streak is greater than best, we update best. That closes our loop. By this point, we have evaluated every single day's contribution to potential profit. And finally, we return the highest profit streak we discovered. This represents the best buy then sell outcome. And that is how this algorithm works. It initializes trackers for the running profit and the maximum profit. Then it steps through each day's price changes, building positive streaks and discarding negative ones. In the end, it captures the strongest upward trend. Efficient, simple, clear. Check. This test case confirms the algorithm's behavior when no profitable transaction is possible. Prices equals 7, 6, 4, 3, 1. Each number represents the stock price for a given day. To earn a profit, a later day must have a higher price than an earlier day. Start at 7 as the initial minimum. Move to 6. The price drops, so we update the minimum. Then 4. The price drops again, so we update the minimum. Then 3. Still decreasing. Then 1. Still decreasing. At no point does the price rise after a lower price. Therefore, there is no day where selling would yield a positive profit. The maximum profit remains 0. The output is 0, matching the expected 0. This confirms that the solution correctly handles cases where no profitable trade exists.
Let's have a quick recap. Breakdown recap. This problem is all about timing your trades for maximum profit. You're given a list of stock prices, each representing a day, and your goal is to find the best day to buy and a later day to sell to achieve the highest possible profit. You can only make one transaction, buy once, sell once, and if no profit is possible, you simply return 0. Assess recap. At first, checking every pair of buy and sell days seems logical but quickly becomes inefficient as the input grows. The smarter approach is to think dynamically, track the lowest price seen so far and calculate potential profits on the fly. This shift from brute force to a single pass solution transforms the problem into an O(n) time, O1 space optimization, fast, clean, and elegant. Structure recap. Our plan followed a simple logic loop. Keep two variables, one for the minimum price we've seen and one for the maximum profit we've made so far. For each day, decide, is today a new minimum, or could selling today beat our previous best profit? Step by step, the loop narrows down the best buy-sell combination automatically. Implement recap. In practice, we brought this logic to life by simulating the market day by day. Each iteration either updated the lowest price or recalculated potential profit, steadily refining the outcome without needing extra storage or nested loops. The program effectively thought like a trader, balancing opportunity and risk in real time. Check recap. When tested with our sample input, the logic held perfectly. Buy at 1, sell at 6, and lock in a profit of 5. Every step confirmed the reasoning. Quick comparisons, instant updates, and a final result that matched the expected outcome. It's efficient and intuitive once you see it in motion. The biggest takeaway here is pattern recognition, spotting opportunities by tracking key values as they evolve. This problem isn't just about stocks, it's about optimization under constraints. Once you master this logic, you'll see it reappear in countless interview questions that reward smart, efficient thinking.